In this video, I'm going to solve an example problem involving surface forces. So we're told that a sled is pulled with a constant velocity using a rope. The tension in the rope is 8.8 newtons. The sled's mass is 4.5 kilograms. Determine the magnitude of surface forces exerted by the ground on the sled. So the meaning of the magnitude of the surface forces, this is going to be the vector sum of the forces that the ground exerts on the sled. So that could be like friction, or it could be the normal force. So first, let's draw a little picture. So we've got a sled, and it's being pulled along the ground by a rope. And it's got constant velocity, and it's moving to the right. So this is our sled, and it's moving along the ground. So let's create a free body diagram of the forces that are working on the sled. So I'm going to represent my sled with a little dot. We know that we have a rope that's pulling on the sled, so that is some kind of tension force. It's pulling to the right. And in the problem, we're told that the sled is moving with a constant velocity, so it's not accelerating. That means that according to Newton's second law, if F equals ma, if acceleration is 0, then the force has to be equal to 0. If the net force is 0, then the forces in the horizontal direction have to balance each other out. They have to add to 0. So if we have a positive rightward tension force, then we're going to have an equal magnitude negative leftward force. And what is that force? What is holding the sled back as we pull it? Well, this is, as we've learned, this is the force of kinetic friction. So it's the force of kinetic friction. And what do we have then? So we've taken care of the horizontal forces, and well, we know that gravity is always pulling on the sled. So this is the weight force. And just as in the case with the horizontal forces, we need to have something that's balancing out this weight force because the sled is not moving in the horizontal direction. It's not accelerating. So we know then that the normal force is pressing upward against the sled, and that's what's helping to balance out the weight force. So it's not moving in the vertical direction. Now, when the problem talks about the magnitude of the surface forces, let's look at our different forces. Which of these are due to the surface? Well, the tension force has nothing to do with the surface of the earth touching the sled. The weight force is actually a force that the earth is feeling from the sled. The sled is pushing downward on the earth. So this is not a surface force. This is a force that's exerted by the sled on the earth. Even though the gravity itself is caused by the earth, the one who's feeling that push is the earth. The earth is feeling the push of the sled against it. So our other surface force then is the normal force. This is what the sled feels from the earth pressing up against it. So these two forces, the force of kinetic friction and the normal force, are what make up this surface force. And when we think of magnitude, well, we can remember that we can find the magnitude of two vectors, and it's the hypotenuse of a right triangle. So this leftward force would be one side, this upward force would be the other side, and the magnitude would look like this. So we could draw the leftward force again. This is the force of kinetic friction. We have the upward force. This is the normal force. Well, then the sum of these two forces that makes the hypotenuse, the sum of these two vectors, is this vector right here. And you might be like, wait a minute, that's not a triangle. We can move this normal force over, and then you'll see that it is indeed a right triangle. So here's the leftward force. Now we're moving this normal force over here to the left, just so we can picture this triangle. And then this is the magnitude. So This is force of kinetic friction. This is the normal force. And now this is the magnitude of the surface forces. Okay, so we're looking to find the magnitude of the surface forces. I'll call them F sub S. And it is the vector sum of F sub K and N, the normal force. If you look at this, if we've basically completed this tail to tip method, and then we drew the sum from the tail of F sub K to the tip of the normal force. So we're looking to find this magnitude of these surface forces. So how do we do that? Well, let's start with what we know. Let's write in what we know. Okay, so the sled, the mass is, let's see, 4.5 kilograms. So we know the mass of the sled. That's going to be useful. And we're told the tension force. So the tension force is equal to 8.8 newtons, and that's pointing to the right. And, well, what is the weight force? We're not told the magnitude of the weight force, but we have to think back to our formula. Well, what is the formula for the weight force? And the weight force is equal to mass times acceleration due to gravity. And the acceleration due to gravity is equal to, if it's pointing downwards in this case, negative 9.81 meters per second squared. So I know G, and I know mass. It's 4.5 kilograms, so I can find the weight force. So I'm going to go ahead and plug these values in. So the magnitude of the weight force is equal to 4.5 kilograms times G, which is negative 9.81 meters per second squared. And I'm going to put that in my calculator. So 4.5 times negative 9.81 is going to be, to two decimal places, this is going to be a negative 44.15, and we have kilograms times meters per second squared. That is the definition of a Newton. So this is the weight force, and it's pointing downward. Well, we said that the sled is not moving in the vertical direction, so the magnitude of the normal force has to be equal to the magnitude of the weight force, because F net in the y direction is equal to 0. It has to be equal to 0, and we also know that F net in the x direction is also equal to 0, because this is not accelerating. So if it's not accelerating, according to Newton's second law, A is 0, we have no acceleration, then F must be 0. Okay, so the normal force, the magnitude, is equal to the magnitude of the weight force. So we have the weight force's magnitude. We know then that the normal force is a Newton's third law pair, an action-reaction pair, and therefore the normal force is going to be equal to the positive, the opposite sign of the weight force, which is 44.15 newtons, and it's positive because it's pointing upwards. Okay, so that's good. That's one of the surface forces, and we need both of the surface forces to figure out the magnitude of the forces that the ground is exerting on the sled. So that's one of them. That is the normal force. Next, I have to figure out this force of kinetic friction. And just like we did in the vertical direction, I'm going to figure out the force of kinetic friction because I'm told the tension force. So the tension force is just positive 8.8 newtons to the right. Well, then I know because we now have F net also in the x equal to 0. Well, then the magnitude of T, the tension, is equal to the magnitude of F sub K. So I know T. T is in the positive x direction. It's 8.8 newtons. So the force of kinetic friction is the negative of T. So this is negative 8.8 newtons. And that is the second piece we need to find the magnitude of the surface forces. We now have both components. We have the normal force and we have the force of kinetic friction. And now all that's left is to find the hypotenuse of this right triangle using the Pythagorean theorem, which we know that a squared plus b squared equals c squared. So c is equal to the square root of the left-hand side. If we take the square root of both sides, then we're left with c is equal to the square root of a squared plus b squared. So c, now we've called this F sub s, this magnitude of the surface forces. So the magnitude of the surface forces, this is just a name that I gave it. So this is this hypotenuse of this right triangle. So the magnitude of these surface forces is equal to the square root. Now I need to square both sides and add them. So we have the normal force, which is 44.15 newtons squared, plus we have the force of kinetic friction, which is negative 8.8 newtons squared. And that is the quantity that we need to solve for now. So I'm going to have a newton squared, and let's see what happens when I square these values. So this becomes still the square root, and I need to take 44.15 squared, and to 2 decimal places, this is 1949.22 newtons squared. So I squared both the numeric value and I squared newtons. Now I have to square the negative 8.8 squared is going to be positive. So 8.8 squared is equal to, this is going to be 77.44. And again, it is newtons squared. So these are both the same type of number. We have a factor times a newton squared and a factor times a newton squared, so I can add these. So I'm going to add the 1949 plus the 77, and this then becomes, we have 2026.66 newtons squared. And now I take the square root of both of these, and this is going to be equal to now 45.02 newtons. So I took the square root of the numeric value and I took the square root of the factor of newtons squared. So this leaves me with 45.02 newtons. This is the magnitude of the surface forces of the ground on the sled. So this is how much the ground is forcing on the sled. So you have an upward component and you have a leftward component, and the Pythagorean theorem tells us that the value, the magnitude of these two, the vector sum of these two is then 45.02 newtons.